Yeah, thank you for the introduction. Hi everyone, I'm Drew. This work was done with the floquet group at the University of Maryland in association with collaboration with Dr. Nikhil Chopra's group. Dr. Chopra specializes in algorithms. His group created the algorithm Iteratively Preconditioned gradient descent in the context of machine learning and robotics, and here we're applying it for quantum circuit optimization. So just as an overview before getting into the nitty-gritties about what we're working on, in general, we can create quantum circuits using what we call single and 2-qubit gates. And so over there we have, an idea of what a quantum circuit can look like. You have little blocks that show gates and operations you can make on single qubits, and then you also have operations that you can make on multiple qubits. And the collection of these different gates gives us circuits. We can collect circuits together to create different subroutines to achieve desired outputs or desired purposes. So an example of this that's commonly used is Shor's algorithm. Shor's algorithm is an algorithm that allows us to find the factors of very large numbers by providing better guesses for each iteration of the algorithm for what those factors could be. So it provides speed up that is beyond comparison to any normal computer, and is why it's a topic of hot debate because of its possibility to break RSA encryption, since our current standards are reliant on being able to find the factors of these very large encryption numbers. This algorithm can find those factors very efficiently. But if you'll notice, within quantum circuits, so this is the quantum circuit of Shor's algorithm, we have bigger blocks that are abstracted. You have this QFT block over here. And so we can represent circuits within other circuits through these bigger blocks. So this QFT block over here is another circuit within the circuit. And so we collect a bunch of subroutines together to create a quantum algorithm. But the issue is this particular subroutine, we call it the quantum Fourier transform, is a very challenging subroutine to implement in general. And so I guess what makes a challenging subroutine is, well, within that block, the number of multi-qubit gates, so the number of gates between different qubits, the depth of the circuit, how many gates there are in our circuit. The longer they are, the harder that circuit is to implement to high fidelity. The connectivity, sometimes we want to entangle one qubit with another qubit, but it's physically not possible on our chip. And so that's something to consider. And the gates themselves. Sometimes we want to just rotate a qubit by a certain angle, and that's relatively easy. Other times we want to perform operations that are not as easy, like a controlled Rx rotation or a swap gate are two examples of more challenging gates to implement. And so all of these factors prevent subroutines from being implemented on our current computers, which are in the NISQ era, the noisy intermediate scale quantum era. So the question is, if we have these limitations with our current systems, how can we run these challenging subroutines? And the answer is, although we cannot, we can approximate them to a relatively high fidelity. And so one option to do so is through what we call a sort of hybrid circuit optimization, where we have our classical, our normal computer that decides what angles gates should be on a circuit. We then run that circuit on a quantum computer or a quantum computing simulator. We look at the output and we say, okay, does the output of our quantum computer match what we want our output to be? And if it doesn't, we feed that information back into a normal computer, we recompute these angles, and we continue this process until we arrive at our desired solution. So it isn't necessary that we send jobs to a quantum computer to do this. We can use a quantum computing simulator to do so as well. And so in this process, there are two approaches. There's what we call a gradient-based approach and a non-gradient-based approach. And today, and for this work, we'll be focusing on the gradient-based approach. And so within gradient-based optimization, in general, from the context of machine learning, the idea is that you have some function, and I'm going to call this function a cost function, and you're trying to find the minima of this function. And so one method of doing that is through taking a set of parameters, computing the gradient at where your point is, and finding where you can minimize that gradient to find your point of convergence. So in this function over here, you might start out somewhere over here, and as you continue to compute the gradient, you'll find that, hey, your minimum is in fact down here. that's where your gradient value equals 0, and you know that whatever parameters you're applying into this function give you an answer so that you're at the minimum point. Well, the challenge with this is that with this type of optimization, this is called a first order optimization because you're only computing the gradient and you're doing nothing else. And the challenge is most cost functions don't look like this. They look something like this on a 3D scale, where you have lots of local minima, lots of local maxima, and areas of what we call barren plateaus. Areas where you're not at the minimum of a function, but you're in a location where your gradient is 0, so your algorithm doesn't know where to go because there's no way for it to find out that, oh, this is the minimum over here, as opposed to being stuck somewhere else. And so what do we do about this? Well, we have second order methods. We have, so these are the effects of lower order techniques. So gradient descent is what I showed in that page before. Atom is another example, whereas you can see here, maybe the final value for cost it reaches is this local minima as opposed to being down here. And so these are the challenges with first order gradient based approaches. They get stuck at local minima, they don't go beyond that. And so that's where we come to higher order techniques. LBFGS is one of them, Newton-Raphson method's another, to be able to compute cost functions that are more complex. These are also trying to minimize the value of your gradient, but you're also computing the Hessian, which I call the gradient of the gradient, and you're using that to find your lowest value as well. In fact, whenever your algorithm thinks it's at a local minima, it calculates the eigenvalues of your Hessian, and if those eigenvalues are possible, it lets you know that, hey, I'm at a local maxima, and if they're positive, you're at a local minimum. If they're negative, you're at a local maxima. And you continue this process until you find another minimum. The issue is, and so each step of that looks like this, where it's like the gradient, it's like the first order method, except now you have your Hessian matrix as well in addition to your gradient. So you have both of these. But in order to do that, in order to compute eigenvalues in general, you need to take the inverse of a Hessian. And taking the inverse of a matrix is very computationally costly. If you are trying to optimize a circuit with 64 parameters, you're going to have a very large matrix you're continually trying to find the eigenvalues of, and that's going to be very costly, inverting it each time. So that's one of the challenges of using a higher order method for quantum optimization. The other issue is that if your Hessian itself has a large ratio between its largest and its smallest eigenvalue, we call that ill-conditioned, in that your algorithm does not know at what rate it should converge in different directions. So these are the two challenges with higher order optimization. So although higher order methods are better at going through more complex cost functions, the challenge are these two, inverting a Hessian and the ratio of your largest and smallest eigenvalues. And so how do we get the benefits of this higher order optimizer while addressing these issues? And so one method of doing that is through what we present over here, iteratively preconditioned gradient descent. The way it works is that we have what we call a preconditioner matrix to approximate the Hessian each time, rather than trying to calculate the Hessian each time. And so initially, we choose a set of parameters to start at with an initial identity matrix as our Hessian. And each step, we update our guess for what parameters will minimize our cost function, and we update the matrix each time using these hyperparameters. And we continue to do so until our cost function is minimized. So we repeat this process until our cost function is minimized. And so the advantage is that, well, now you're no longer computing the inverse Hessian in each step, and you're also improving the conditioning of each step because you're updating your preconditioned matrix in each step according to these factors. And these hyperparameters are functions of our maximum and minimum eigenvalues to help with making sure that our matrix is what we call well-conditioned. And so when this has been applied to classical settings, we find that for convex functions, like the function you saw at the very beginning, just a nice parabola, it converges in linear time. And when you have a unique solution, it converges superlinearly. Although most quantum algorithms don't have unique solutions, you can make infinitely many circuits to get the same output. The superlinear convergence is still important to us when we try to find the most optimal solution for a matrix. And so that's what IPG does. And so now I present to you our experimental, our hybrid loop. So what we have here is we're trying to achieve a particular quantum state. And so we have a cost function that establishes how far our current state is from our desired state. We then use this cost function, we apply this to our optimizer to determine what parameters should get sent to our quantum simulator, and then we run a simulated quantum circuit with these parameters. The circuit output then gets fed back to the cost function to compute a new cost to feed into the optimizer, and we repeat this process until our circuit approximates the state we want to get to a very high fidelity. So states that are currently challenging to have exact solutions to, but we're able to approximate and run on these computers. And so with that in mind, once we've completed the optimization loop to evaluate the effectiveness of the solution, we send our parameters to an actual quantum computer to see, hey, are we getting the output we expect to get? And so just as a bit of an overview, our cost function introduces local maxima, minima, and barren plateaus. So the reason we have this complex tomography, or what we call loss landscapes, is because of our cost function. If we change this function drastically, the shape that our function is the shape our optimizer traverses drastically changes. And that's what our cost function does. Our optimizer, well, for us, we're using what we call a penny lane PyTorch interface. Penny lane is a quantum computing package that is available. And PyTorch has automatic differentiation built in, so we don't compute our gradients. The gradients are automatically computed through a differential technique called back propagation, where the error accumulated over each gradient with respect to time continually adds up and is fed into the optimizer. So gradients are computed automatically through this interface. And then I've been using the word ansatz, and ansatz is just a fancy way of saying circuit. So this is the circuit we are trying to optimize. It's what we call a strongly entangling circuit, because each layer of our circuit, so each dotted box, has a set of rotation angles on each qubit, as well as a set of C0 gates to entangle each qubit to one another. And we can apply L layers of this until we get a circuit that achieves the extent to the Hilbert space we want to achieve. I should note, we use this as a general ansatz because we're evaluating the optimizer, not our ansatz itself. And so you would change the circuit depending on the application of your problem. For example, if you're trying to use a quantum computer or quantum algorithm for a chemistry problem, you might use an ansatz that only has particle conserving rotations or Gibbons rotations. You might use that specific ansatz, but here we use a general ansatz since we're evaluating the optimizer itself. And so the first state that we evaluated were the 5-qubit G8Z state and the 4-qubit W state. The 5-qubit G8Z state means that my output should be all zeros and all ones. So if I have a histogram with how many times all zeros were put on and how many times all ones there were, I should see peaks on either side of my graph. And the 4-qubit W state, which means that I should see peaks at the 0001 state, the 0010 state, 0100, and 100. 1000. And so those are the two states we're trying to achieve using this ansatz over here. So we're changing these rotation angles over here to try to get this circuit to output these results over here. And so the cost function we use is just the real part of the inner product between the output of this quantum circuit and the exact state, which is this over here. And so those are the states we're trying to achieve. That's the cost function, and that's the ansatz. And so the results for this are as followed. When we applied this process to conventional optimizer they use, gradient descent and atom, our convergence was about 4 orders of magnitude closer to the exact solution than those optimizers themselves. You can see this in the plots. This optimization was done on a noiseless quantum computing simulator, and the exact state you expect is a peak on one side and a peak on the other side of your graph. So IPG essentially achieves that exact state, while the other optimizers struggle as you have values between your 00, your zeros and your 1 state, which should not be present. And so when we take the parameters that were given by IPG and put them into a quantum computer, we get the following. And so because this is run on RE01, a noisy quantum simulator, and this was also run on a quantum computer, we find that we essentially achieve the GHZ state. We have our large peaks as we expect, but we have lots of noise as well. But when we compare that to, let's say, so the green bars represent the data we got from IPG, so the parameters that our algorithm put out, and Atom are the algorithms that that optimizer put out. And you can see that there's a difference in that the green bars are more closely aligned with the GHZ state than the orange bars, showing superior convergence even in the presence of noise, with the bars being of the same height as we expect, and there being minimal noise between our 0 and our 111 state. And so more accurate states achieved by this. And then what we then do is we try to achieve the W state. And remember, the W state, we're looking for peaks only when there's 1 in our output. So we're expecting 4 peaks at most. And when we do this optimization with our algorithm, IPG in green, gradient descent in Atom, and then we also include a higher order optimizer, LBFGS, we also see superior convergence in that side, where we also have an about 6 order of magnitude difference between the outputs those algorithms brought out versus our outputs. You can see that presented on the graph, because then when we run these parameters on a noiseless quantum simulator, the outputs from the other algorithms produce distinct peaks, but have lots of noise beyond those peaks that are non-negligible, compared to us, where we only have 4 peaks and no noise elsewhere. And so when we then take these parameters and we apply them on a quantum computer to achieve the GHZ state, we find the following, where we have these 4 peaks as we anticipated, and we do have some amount of noise, but considerably less than Atom over here, where Atom also has 4 distinct peaks, but of varying amplitudes when they should all be the same amplitude and a lot more noise. In fact, our run of the W state on a quantum computer through Atom, through IPG, produced better results than the optimized states on a noiseless simulator, which says quite a bit of the difference in our levels of convergence. It also converged more quickly, 26 less iterations to achieve its local minima. And so the fact that this algorithm was able to output the W state using this ansatz on a quantum computer and have results better than the other algorithms on a noiseless quantum simulator is quite remarkable. So we're very proud of that. And so that was the W state over there. And the final portion of optimization was a full unitary. So this entire time we've been trying to optimize for particular quantum states. But sometimes if you have a subroutine, you want your whole unitary to be preserved so that whatever input you throw at the unitary has the same outputs. For example, with Shor's algorithm, we want to preserve the entire quantum Fourier transform because we don't know what the inputs for it will be. We need the entire unitary to produce the same results rather than just one column of it. And so we did just that with the 3-qubit quantum Fourier transform, which has, the unitary has this form over here. And we used an element-wise cost function elicited over here. And what we also noticed with cost functions, just to put into perspective, is that simply by squaring the terms in our cost function, we achieved a 3 order of magnitude greater convergence than without squaring our cost function. So changing nothing to our cost function except saying, let's run it again, but just square our cost function. And at first it might seem strange as to why would you see superior convergence just by squaring a cost function, but it makes a lot more sense once you look at it, because by squaring it, your function becomes smooth and analytic in the complex plane. Quantum vectors are complex valued, so it makes sense that you want your cost function to be analytic to some portions of your complex plane at the very least. And so this is just to illustrate complex cost functions have a huge impact on the output of a circuit in general. Our ansatz is as followed. It's larger than the ansatz we used for the state vectors because, again, we're trying to preserve this entire matrix rather than just a particular column vector of probabilities. And so when we run that, we see the following. And so when we run this optimization using each algorithm over multiple epochs. And so when I say epoch, I mean we run the algorithm with with random parameters each time. And so each epoch has a different set of parameters. So when we run 3 epochs of each optimizer, we find that, in fact, for unitary optimization, it appears that LBFGS achieves about the same cost as all the other optimizers, but in rapidly less time. But this is for the best case scenario. You won't always start at a random initialization that gets you this level of performance. So then when we average the epochs, so we average multiple epochs of convergence, we find that, in fact, IPG was the most consistent in its convergence. And looking closer, although it's marginal, the cost achieved by IPG is about twice as small as achieved by the next best optimizer as well. And so if we look at the average values over time, although LBFGS, its best output was able to get to the lowest cost in the least amount of time, on average, it fluctuated a lot more. We see the same with Atom on this graph as well, where our average is sort of tending to the middle, but our individual runs, as represented by the dotted lines on the graph, vary quite a bit. While the green line with IPG, the dotted lines, the dots are very close to our average runs. So we see consistent convergence with IPG to a marginally lower cost, which we were very happy to see. And so we then run the parameters for the 3-qubit quantum Fourier transform on an actual QPU. And this is where things get interesting. So if you run the quantum Fourier transform without any initialization, set all the initializations to 0, you should expect an even superposition of each of each state. So you should see over 1,000 shots, you should see 125 shots for each output. And this optimization is close to that, but certainly isn't as close as we would want it to be to run the quantum Fourier transform. The reason for that is what I mentioned earlier. We pick an ansatz, we pick this circuit back here based off of the problem we're trying to solve for. So if we were trying to optimize the quantum Fourier transform for real, we wouldn't be using this ansatz, we'd be using an ansatz that is more optimized. And so in this case, we see values close to 125 shots, but not exact. And this was run on IonQ's Aria computer. And on their older computer, Harmony, we see poorer performance on their 11-qubit Harmony system versus their 29-qubit newer system. You can demonstrate the effect of the quantum Fourier transform through trying different initialization states and seeing where your peaks resolve. And so to test that, what we first did was we tried an even superposition of all qubits. We set all the qubits to an even superposition and ran the quantum Fourier transform. When you do this, ideally, you should only expect the 0 state to appear. And that's just what we see over here, where we see 800 shots on the 0 state and less than, at most, 50 shots on our 011 state. But we still see what we expect. And then to demonstrate its performance, we then apply a Pauli-Z operation on the 3rd qubit of our quantum Fourier transform, which is the equivalent of changing the phase of our 3rd qubit. And when we do so, we expect to see an output of 001, which is shown by state 4 over here, having a peak at the 001 state. So the quantum Fourier transform with this ansatz does perform as expected, despite when we run it without any initialization, we don't see a consistent 125 shots per state. And so I guess the main takeaways is that what we did was we approximated 3 different quantum subroutines: the W state, the G and C state of the quantum Fourier transform. We tried to approximate these using an ansatz, and we did this with 4 different optimizers: Atom, gradient descent, LBFGS, and our optimizer, IPG. Our results were that for state vectors, we found an orders of magnitude difference in convergence with IPG compared to other traditionally used optimizers. And for the unitary itself, we found that it converged consistently over multiple epochs, even though its best convergence was not the fastest. And then we took our parameters and evaluated their performance on an actual QPU. and ran that. And so with that, I'd like to thank Dr. Avik Dutt from the Floquet group, Dr. Nikhil Chopra from the Department of Mechanical Engineering, and Kushal Chakraborty, who is a PhD student with Dr. Chopra that worked on this algorithm. This work was funded by IMQ and the National Quantum Lab at the University of Maryland. And so thank you very much.